It is September 23, 1999. Mission control at NASA's Jet Propulsion Laboratory in Pasadena, California. For 9.5 months, a spacecraft called the Mars Climate Orbiter has been traveling through the solar system. 416 million miles, launched the previous December. Built to study the Martian atmosphere, track water vapor, and monitor the planet's climate in ways no mission had attempted before. This morning, it is scheduled to fire its main engine and settle into orbit around Mars. The room is tense but confident. This is a routine, well-rehearsed maneuver. Engineers have run the numbers. Everyone trusts the numbers. At 9 a.m., the engine ignites, exactly on schedule. 9 minutes later, the spacecraft passes behind Mars, as expected, and radio contact is briefly lost. Also expected. Controllers wait for the signal to return. It doesn't come back. They wait longer. Still nothing. Slowly, the room understands what has happened. The orbiter did not settle into orbit. It flew too close to the planet. So close that Mars' thin atmosphere tore it apart, or sent it skipping back out into space, lost forever. Either way, the mission is gone. $327.6 million. 9 months of travel. Gone in less than a minute. And when investigators finally traced the failure back to its source, what they found wasn't a broken engine, a software crash, or a design flaw in the spacecraft itself. It was a units mismatch. One team's software calculated in pounds. Another team's software expected newtons. Nobody caught it. Nobody checked. And a spacecraft that had survived 9 months and 416 million miles of empty space was destroyed by a math problem that a first-year engineering student is taught to avoid on day 1. This is the story of the Mars Climate Orbiter. To understand how this happened, you need to understand how a modern spacecraft mission actually gets built, and just how many hands touch it before it ever leaves the ground. The Mars Climate Orbiter was part of NASA's Mars Surveyor program, designed to work alongside a sister mission, the Mars Polar Lander, to study the Martian climate, atmosphere, and surface in unprecedented detail. NASA did not build the spacecraft itself. The agency contracted the design and construction to Lockheed Martin Astronautics, based in Colorado, while NASA's own Jet Propulsion Laboratory in California retained responsibility for navigation, plotting the spacecraft's course and guiding it to Mars. This division of labor was completely standard. NASA missions routinely involve multiple contractors and multiple NASA centers working in parallel, each responsible for a different piece of an enormously complex system. The Mars Climate Orbiter needed small course corrections throughout its 9-month journey, brief firings of its thrusters to keep it precisely on the calculated path to Mars. The software controlling those thrusters, built by the Lockheed Martin team in Colorado, calculated the force those thrusters produced and reported that data back to the ground. Here is where the problem was built in, silently, long before launch. The software Lockheed Martin's engineers wrote calculated thruster force in pound-seconds. NASA's navigation team at the Jet Propulsion Laboratory, receiving that data and feeding it into their own trajectory models, expected the incoming figures to be in newtons. Nobody translated the numbers. Nobody caught the mismatch. The data simply passed from one system to the other. Unit label unchanged, meaning subtly, catastrophically altered. The difference between a pound of force and a newton is not small. A pound force is roughly 4.5 times larger than a newton. Every single time the software reported a thruster firing in pound seconds, and the receiving system logged that number as though it were Newton seconds, the spacecraft's guidance model registered a force reading that was off by a factor of nearly 4.45. For 9 months, that error compounded quietly, correction after correction, so gradually that it barely showed. Small trajectory adjustments made throughout the journey were each calculated against a subtly false understanding of how hard the thrusters had actually pushed. What makes this story remarkable isn't just that the error existed, it's how long it survived, undetected, inside a process built specifically to catch exactly this kind of mistake. Throughout the journey to Mars, the navigation team noticed something odd. The spacecraft kept drifting slightly off its predicted course, requiring more frequent correction than expected. It wasn't dramatic. It wasn't alarming enough on its own to trigger a full investigation. Spacecraft navigation is not perfectly precise. Small discrepancies between predicted and actual position are normal, and engineers routinely make adjustments to compensate. But this drift had a pattern. Investigators later found that engineers on the ground had, at multiple points during the mission, actually flagged discrepancies between where the spacecraft was predicted to be and where tracking data showed it actually was. Those flags were raised, they were discussed, and in each case, the team concluded the differences were within an acceptable range, or attributed them to other, more routine sources of navigational uncertainty. Nobody traced the drift back to the unit's mismatch because nobody had reason to suspect that two major systems, a spacecraft contractor's thruster software and NASA's own trajectory modeling software, were quietly speaking two different mathematical languages to each other. This is precisely the kind of failure that formal review processes exist to catch. NASA missions are subject to extensive peer review, verification, and validation procedures specifically designed to surface exactly this type of cross-system inconsistency before it can cause harm. The investigation that followed the loss of the orbiter found that those checks, in this case, simply had not been rigorous enough. There was no single moment where someone was asked, directly and specifically, "Are you certain the units match on both sides of this data handoff?" and answered incorrectly. There was instead an absence, a check that should have existed and didn't, a question that should have been asked and wasn't. As the spacecraft closed in on Mars in September 1999, the accumulated effect of 9 months of subtly mismatched calculations had shifted its planned trajectory significantly. The mission had been designed to bring the orbiter to within roughly 140 to 150 kilometers of the Martian surface at its closest approach, close enough for a safe, stable orbital insertion. Final tracking calculations, made in the days before the critical engine burn, indicated something was wrong. The spacecraft's actual path looked as though it would bring it far closer to the planet than planned. Engineers debated the numbers. Some considered a further correction. Ultimately, the decision was made to proceed with the orbital insertion as scheduled. On September 23rd, the engine fired. The Mars Climate Orbiter did not settle into a safe orbit at 150 kilometers. It came within approximately 57 kilometers of the Martian surface, inside the altitude that mission engineers had calculated the spacecraft could structurally survive. At that altitude, atmospheric drag and heating would have been severe enough to destroy the orbiter, tearing it apart or burning components away, possibly sending whatever remained skipping back out into an unusable trajectory through space. Either way, the mission was over. 9 months, 416 million miles, and $327.6 million, undone by a mismatch between two units of force that nobody along the chain had thought to double-check. NASA convened a formal investigation, known as the Mars Climate Orbiter Mishap Investigation Board, to determine exactly what had gone wrong. Its conclusion was direct. The proximate cause was the unit's error, pound-seconds delivered by Lockheed Martin's software, interpreted as Newton-seconds by NASA's navigation system. But the board and NASA's own leadership were careful to make a distinction that would echo through engineering education for decades afterward. Dr. Edward Weiler, NASA's Associate Administrator for Space Science at the time, put it plainly in the agency's own public statement, following the investigation's preliminary findings. "People sometimes make errors," he said. "The problem here was not the error. It was the failure of NASA's systems engineering and the checks and balances in the agency's processes to detect that error before it caused catastrophic damage." That distinction matters enormously. A single engineer choosing to express force in pound-seconds instead of newtons was not, by itself, a catastrophic mistake. It was an ordinary, human, entirely explicable choice made by someone working within one part of an enormously complex system. The catastrophe was that the system surrounding that choice had no reliable mechanism to catch it before it mattered. No single person was identified as solely responsible. The investigation instead pointed to a chain of missed opportunities: inadequate verification of the interface between two contractor systems, insufficiently rigorous review of the trajectory anomalies noticed during the journey, and an overall process that assumed compatibility rather than confirming it. The loss of the Mars Climate Orbiter did not happen in isolation. Just 10 weeks later, its sister mission, the Mars Polar Lander, was lost during its own descent to the Martian surface. In direct response to the Mars Climate Orbiter failure, NASA overhauled its approach to interface verification between contractors and internal teams, mandating far more rigorous, explicit documentation and cross-checking of units, formats, and data definitions at every point where one system's output became another system's input. The spacecraft itself is gone. What survived was the lesson. Subscribe to Error Code Human, featuring new documentaries every week.